Welcome everyone, and thank you for attending the Foundation webcast today titled Advancing the Seawater Desalination Knowledge Base. The webcast today is presented in partnership with the WateReuse Association. My name is Kristen Vandenhavel, and I'm a research manager here at the Foundation. I manage our agricultural reuse and desalination research, and I'm excited about today's presentation. Now, before we get started and introduce today's speakers, just a few housekeeping items to go over. Be sure to submit questions through the question box at any time throughout the presentation. It can be found on the left side of your screen. We will do a Q&A near the end of the webcast, and if we do not get to your question today, we can follow up and respond via email. There are 3 post-event questions that will pop up at the end of our webcast. Please be sure to answer those questions so we can hear your input and also help us improve future webcast presentations. The slides will be available for download at the left side of your screen following the webcast, and they will also be available on our website within about 24 hours of the event at waterrf.org. Here's a reminder of how you can download the presentation on your screen there, and a nice screenshot of the question box. Please feel free to submit questions at any time, and we would be happy to answer those. So we're excited to highlight 2 recently published desalination-related reports during our webcast today. We have 2 great speakers lined up for you. Our first speaker is Dr. Joe Giacangelo. Dr. Giacangelo is a Vice President and Director of Research for Stantec, and he will be presenting on the project Pretreatment for Seawater Reverse Osmosis, Existing Plant Performance and Selection Guidance. And our next speaker will be Dr. Brent Alspaugh. Dr. Alspaugh is the Principal Environmental Engineer and Director of Applied Research at Arcadis, and he will be presenting on the Carlsbad Desalinated Seawater Integration Study. And we will have approximately 30 minutes at the end of the presentations today for question and answer. Please remember to submit those questions so we can jump right in when we're ready to go. Now I would like to hand it over to our first speaker. Over to you, Joe.
Thank you, Kristen. Today I'll be talking about a project, as Kristen mentioned, on pretreatment for seawater RO. But before I begin, I'd like to acknowledge my co-authors of the project, Nikolai Vuchkov from Water Globe Consultants, Mohammed Badruzman, who was with Stantec at the time, and Lauren Weinrich from American Water. What I'll be presenting today is some background, followed by the research approach to the study, and then I'll discuss the full plant questionnaire and the interview site visits that we conducted. And then finally, I'll describe the construction of a pretreatment planning tool that was also part of this particular study. So what are the drivers? What were the drivers for this study? Well, as we all know, pretreatment is key to successful operation of seawater desal. In fact, if you ask a lot of engineers or utility personnel or operators, what are the 3 most important components of successful seawater desal operation? They'll say number 1 is pretreatment, number 2 is pretreatment, and number 3 is pretreatment. So pretreatment does play a significant role. And then the long-term reliability of the downstream RO membranes impacted by the treatment really pretreatment has not been systematically reviewed and documented to any great extent. So that was another driver. And finally, there's also an influence of non-water quality parameters and non-process factors on the selection of pretreatment, and those also were not reported. So these were the main reasons for the study. The specific research objectives were 1, to evaluate the impact of the feedwater quality on the performance of pretreatment technologies and the RO processes, then to collect full-scale data on the performance of various pretreatment technologies and operational data on RO, and then finally to better understand and identify and assess the criteria used for selecting pretreatment technology at full scale. And then finally, based on all the information that we obtained from the study, we then develop a tool to provide guidance on pretreatment process and selection and design for those that are considering seawater RO. Now, in terms of the approach of the study, the work plan was composed of 3 tasks. The first task was a literature review, and we went into the peer review, the gray literature, manufacturer, technology provider literature, and amassed it all to put together a literature review, which you can see in the first part of the report. Also, if you're interested, this review has actually been published in Desalination by the project team, so that also presents an opportunity to read about what the latest is on the selection of pretreatment technologies. The second task was to conduct a questionnaire where we sent questionnaires to the participating utilities, and we asked them about a number of different things about their plant. We looked at background information, of course, but also asked them about the plant capacities, types of intakes, asked them for schematics, water quality, information on operation, information on some of their lessons learned, and design aspects, et cetera, et cetera. So this was filled out initially by all of the utilities participating in it. But we also know that that in addition to just getting information from a questionnaire, there's a lot more information that can be obtained if you actually talk with the operators and plant designers. And so our third task focused on doing facility audits, where we actually go to the plants and talk with the people, get tours, and understand how their pretreatment processes actually work. And so then we took that information from tasks 1, 2, and 3, and from there we put together assessments of the raw water quality, the water conditioning that occurred, conventional and membrane performance, as well as reverse osmosis performance. And I'll be presenting some of this to you today. So initially, we had 42 plants that we considered to participate in this study, and we made a selection from that to 8 plants. The selection was based on the characteristics of the plants, but also on logistics and those that would be willing to share data, et cetera. And so based on that, we did a final selection of 8 plants. 3 were located in North America, 2 were located in Europe, and 3 were located in the Middle East. Now, the plants could be described by their size. I have it here presented in cubic meters per day. For those that aren't used to cubic meters per day, you can just divide that by 25, and you get that number. You divide it by 25, and you get approximately the million gallons per day. But what you see here is that we have a variety of size plants, from Plant H, which was very small, to a fairly large plant, Plant A, which was about 220,000 cubic meters per day. We also wanted to be sure that we had a variety of different types of intakes in the study, and so we had 6 plants that had open intakes and 2 plants that have subsurface intakes. And then finally, we wanted different types of pretreatment for RO, and so we had 2 plants that employed membrane pretreatment and 6 that employed conventional pretreatment. This slide here describes some of those pretreatment processes for the seawater desal plants that participated. And you can see there's a wide range, generally categorized as conventional and membrane. Plant A used DAF, followed by dual media pressure filter, followed by cartridge filter. Plant B was, again, a media filter, followed by cartridge filtration. Plant C was primarily microfiltration. Plant D employed dynasand filtration, followed by diatomaceous earth filtration, and then CF. Plant E was dissolved air flotation, followed by dual media filtration and cartridge filtration. And then Plant F and G only employed cartridge filtration, and Plant H just microscreen, followed by UF. So this is your key when I'll be presenting the data in terms of the plants here, in terms of their letters. And let's start off with looking at some of the water quality of the source water or the feed water into the plant itself. And this slide here just describes those characteristics in terms of SDI and turbidity. And what we see here is that there's a fairly wide range of SDIs. You can see Plant C had a high SDI in their feed water of approximately 25, with a fairly wide range. And even Plant E had an average of about 11, but all ranged up to well over 30 in terms of SDI. Turbidity also, you can see here that if you look at the turbidity side of the slide, you can see there's some wide ranges of swings of turbidities and for some of these plants, and they actually presented issues associated with pre-treating the water adequately for the RO process, and we'll talk about that in a little bit. The two subsurface intakes, as you would imagine, had very, very low SDIs and low turbidities coming into the plant. Just some other feed water quality parameters, TDS and total organic carbon or total dissolved solids. You can see on the left-hand side in terms of total dissolved solids, many of the plants were around 40,000, a little higher than your typical seawater. Those were primarily plants that were based in the Middle East area or the Mediterranean. And then we have some that are lower in the U.S. and other parts. And internal and total organic carbon, the only 3 plants monitored it, but what you see here is that for that plant C, again, around 1, but had some fairly wide swings from up to about 6 milligrams per liter. So let's talk about how they condition this water quality that I just described. And we know that for source water conditioning, it's often critical parameter for pretreatment to control fouling. And so coagulation and flocculation is used to control the fouling potential of source seawater. Prechlorination is often used to control the growth of sea organisms and microorganisms. Then antiscalants, of course, are added for scaling prevention. But there's also addition of a reducing agent to quench the excess chlorine that's used in some of the pretreatment. So if we look at the plants, in terms of coagulants, what we see here is that for plant A, they used a fairly high coagulant here in terms of iron. And what you see here, they had averaged about 5, but they had swings from 1 up to 10. And that was primarily due to the varying water quality conditions at that particular plant. The other plants had lower concentrations of coagulant that were used. And in addition, that plant A, in order to control some of that water quality coming to the plant, they added about 0.3 milligrams per liter of polymer, but they were at the time trying to reduce that so they would not have to add as much or any polymer at all. Further, no coagulant, of course, was added for the subsurface intakes, and then membrane-based pretreatment operated with and without coagulant, one with and then the other without. So if we look at prechlorination, the plants practice 3 different types: shock, intermittent, and continuous. And this slide here shows some of the concentrations that were used. And you can see for some of them, for example, plant A used a very high dose of chlorine on the order of 10 to 15 milligrams per liter of chlorine in a shock mode. And a lot of that had to do with the biofouling of the intakes. And you can see it was also practiced at plant E, that they also had a concentration average about 8 milligrams per liter, and then some lower concentrations at the other plants. And then plant B, plant C, and plant G, none was added. Now, one interesting observation from one of the plants was that plant C, which used a continuous chlorination dose, they at least anecdotally, saw that the organism appeared to get acclimated to that continuous chlorination dose. But unfortunately, the alternative would have been shock chlorination, but unfortunately they could not do that because of the non-chlorine resistant pipe network. So they were having challenges with trying to control biogrowth. And then also, because we add chlorine, we have to add sodium bisulfite. And you can see various levels of sodium bisulfite that's added to control the excess chlorine, either due to shock or continuous chlorination. But one thing that was observed was that overdosing of the sodium bisulfite as control practice actually increased the AOC levels, which of course increases the potential for biofouling. Underdosing, which was also experienced at one of the plants, can cause oxidation of your RO membranes. So for a lot of these plants, it was a challenge to control that chlorine and the dechlorination process. And then finally, antiscalant was practiced by the plants participating in the study. You can see here some of the levels of the various antiscalants in terms of milligrams per liter, and they ranged anywhere from, well, almost not practiced all the way up to about 3 milligrams per liter. Then 3 plants themselves did not add any. One interesting observation was that the polyphosphonate-based antiscalants in seawater contributed generally to AOC increase. So we have another area for AOC increase in addition to the bisulfite. We know that biofouling is an important component of the overall fouling profiles of membranes. Okay, with that short discussion on what the plants did in terms of conditioning, let's look at their conventional and membrane pretreatment systems. So conventional pretreatment system, of course, is put ahead of the RO plant. This slide shows a schematic of that. And these are some of for the granular media filtration, these are some of the plants, these are some of the design characteristics of the plants. And you see here, I have the design parameters as media type, media depth, surface loading, backwash frequency, and waste stream. And I just want to point out a few of these things, and I should point out also that this is all described in detail in the report, so you can simply look at the full design characteristics there. But in general, in terms of media, they were shallow beds, anthracite and sand, except for one bed, which was a little bit a little bit deeper. This was the Dynasand filters. And then in terms of surface loading rates, 2 of the plants were generally around that, which you see in the literature, from 8 to 10. Those was Plant D and Plant E. One plant, Plant B, was a little bit low at 6.3 meters per hour, and Plant A a little bit higher because of the design criteria, at 14 meters per hour. And the backwash frequencies also varied, as well as the waste streams. So here are some of the SDI values for the conventional plants that I described. So you can see, in general, for plant A, B, and E there, what you see is that the pretreatment did pretty well in producing an SDI of somewhere around 4 or less for the most part. 2 things to point out. One, for some of these, the influent SDIs were fairly variable. And secondly, the cartridge filtration in some instances actually helped improve that SDI. Of course, you don't want the cartridge filtration to improve it too much, which means that your pretreatment is not effective. For plant D, there was more of a variable output in SDI. They range from 2 to about 6. In terms of turbidity removed by the plants, again, this slide here shows that we got very good turbidity removal from all the plants. For the most part, they were reduced down to certainly less than 1, on the order of about 0.2 or so. And except for plant D, where there was some variability in the effluent, primarily because of the high variability in the turbidity coming into the influent. Now here's an interesting observation by one of the plants. This is plant A, and what they found was that they were very susceptible to algal blooms. And what they show here are 2 things. In this plant, what we see here is on those photomicrographs, the algae and the bacteria, I should say, they're bacteria in this case, the bacteria on the surface of the RO membranes. You can see in terms of aerobic bacteria, those are the concentrations in terms of colony-forming units per centimeter squared. So we up to well over 1,000 in some instances, and well over 10,000 in others per milliliter. This is an example of another RO system, RO membrane. Based on their pretreatment. This is plant E, which employs dissolved air flotation, followed by dual media filtration, followed by cartridge filtration. And it really shows a fouled membrane in terms of the excess iron from the coagulant. And you can see here that the virgin membrane there is, you can see it's unfouled, but you do see the presence of iron in that second panel of the fouled particular membrane. So it's the challenge, of course, is to make sure that you're dosing but not overdosing with iron in that case, or iron in the feed water, of course. Now, if we look at the pretreatment system for the subsurface intake plants, plants F and G utilize beach wells as intakes, and they only utilize cartridge filtrations as pretreatment. Their SDI values are typically less than 3.0. And one of the important issues associated with those beach wells is that the hydrogeologic conditions can play a very important role, as the presence of iron and manganese can impact the RO performance. Those particular plants paid a lot of attention to looking at iron and manganese as potential foulants for their RO membranes. For these subsurface plants, this is just some SDI and turbidity values that were observed. What we see here is that you can see they produced, for the most part, SDI values well under 4. Those perturbations, both for plant G, both in SDI and turbidity, were primarily the result of the plant shutdown and startup due to replacement of membranes. Interestingly, plant G monitors the SDI values, and not only the values, but the color of the pads for the SDI analysis to determine which well they should be used to minimize iron loading on the RO system. So they actually, based on those colors, those pads, they'll often change which wells are used for that particular time period. Let's quickly switch to low-pressure membranes as they're employed in a pretreatment. And this is an example of transmembrane flux profile at plant C. It's a membrane-based pretreatment, of course. And what you see here in this looks like a shotgun blast here is all of the fluxes in LMH, and you can see here the variety of scatter. But primarily, if you look at and this is I should say this is a plot of all the banks, MF Bank 1 up to MF Bank 9. Some banks perform better than other banks. But in general, the major issue with this particular plant and why they've got such varying profiles was that the plant itself was designed, there was no piloting involved in the plant. In fact, the designer relied upon a nearby location as a reference plant for which to design this, which was at about 80 to 85 LMH. And unfortunately, at this plant, the water quality at the intake turned out to be substantially different than the reference plant, and as a result, their MF performance is always being often gets degraded because of that high flux that's demanded from the RO system. The lesson learned here is, of course, is that piloting is often very important, and before you're designing your pretreatment plant and your RO system. So careful attention should be paid to the water quality at the site that you're particularly going to be using as your feed water. This is an example of one plant. This is plant C, and they had a large algal problem for many time, and this was an issue particularly with Granular polygramma, and you can see some of the algal concentrations of high as 5 million cells per liter. The microfiltration did not let any pass into the filtrate, but nonetheless, these algae and their exudates often cause fouling of the membrane. We saw that in the previous slide with some of these different fluxes that were incurred. So it's important, again, to look at what the algae is if an algal blooms, even if they're not in blooming at the time that you're thinking about putting in. It's really important to get an assessment of whether there are any harmful algal bacteria species. Okay, so let's turn to RO performance at the plants. This is an example of the first stage seawater RO. 6 of the plants actually used 2 stages. The second stage was for brackish water RO. And what we see here are the average flux and the recoveries of the particular plants. I just want to point out a few things. In general, the average recovery was about 40%, sometimes pushing it up as high as 60% for one of the plants. But then there was also a lower plant, a plant that only had about 35% or so recovery, and that was due to the low recovery, the stringent discharge, concentrate discharge limits. So they actually had to blend that water with actually well water in order to meet those discharge limits. And then finally, there was one plant, that's plant F. Boron was a big issue. It was one of their primary water quality permitted parameters, and so now they went towards, at this point, they went to LG nano H2O membranes that primarily for boron rejection, so boron-specific membranes. This slide shows you an impact of the pretreatment on seawater RO operations. And what I have here are all the plants, the membrane cleaning frequencies, the cartridge filter replacement frequency, and the membrane replacement frequency. And I won't go through all of this. This is all in the report, but you can see that there's fairly wide ranges. In red here, I have some of the poor performances on membrane cleaning frequency and cartridge replacement frequency. And when we look at membrane replacement frequency, one plant was actually replacing it 25% of the RO membranes per year, so fairly high. But many also perform very well. And for example, Plant A had a membrane cleaning frequency of every 6 months and only about 10% RO replacement frequency per year. So I'm going to turn now to a pretreatment tool that was constructed based on the data that we received from the plants, based on the literature, and based on the other information that we were able to obtain. And the pretreatment tool, the objective was to assist water utilities in the selection of seawater pretreatment systems, to provide guidance. And this tool, what it asks for is general plant information as an input file, the raw water quality information, and then based on that and some other information, it'll provide recommended conventional or membrane-based pretreatment alternatives. It'll provide effluent water quality information specific for an intake type and selected pretreatment alternative. It'll provide some design information for guidance, and it'll compare the alternatives based on non-water quality related information. So you'll have a comparison of not just technical numerical information, but other things that may also play into the selection. And finally, it provides many guidance worksheets on various water quality aspects, system design, and operation. And I'll just go over this briefly, what some of this tool looks like. So this slide here, and this is an Excel-based tool, so it's fairly easy to use. One of the basic sheets is the general description worksheet, and it asks for things like the desalination capacities, the intake types, or whether it's surface or non-surface intakes, and then it also asks for water quality in terms of input. It asks for SDI, TOC, parameters that most utilities that are considering this should have. And probably most importantly, it asks for information on the expected algal cell counts because, as we know, as our plant information showed us and the anecdotal information that we found during this study, that the algae counts are very, very important in trying to understand what kind of pretreatment should be used for seawater RO. From that information, the pretreatment tool will provide recommended pretreatment alternatives in terms of conventional treatment. In this case, you can see here for this particular example, it recommends DAF followed by dual media filtration, followed by cartridge filtration, or membrane, or membrane-based treatment. So there'll be two options with the various different pretreatment processes ahead of the membrane-based treatment. And then, in terms of the tool, what it'll also output for you on a screen is the actual flow diagram of the particular pretreatment, whether that be conventional or membrane-based pretreatment, and it'll provide an estimated water quality, and then also provide you with typical doses that could be employed with these particular systems based on the process chosen. And then it also provides, if you look down on that those two gray icons on the bottom, it provides water conditioning guidance. So clicking on that will bring up a screen with looking at all guidance associated with water conditioning. And then the one to the right, the icon to the right, will provide conventional membrane-based pretreatment information. So you can then, it will help you make that selection. This is just some of the other output. The output in terms of design criteria. Again, it provides schematics. It'll provide typical design specifications based on what was chosen. And in this case, you see DAF, dual media filtration, and membrane filtration. And then under those icons on the bottom, the gray icons, it'll actually give you design specifications for full-scale plants that are in the ground around the world. In addition, it'll provide process-based comparisons of sedimentation versus DAF, gravity versus pressure, pressure membranes versus vacuum filtration. So it'll give you a real understanding of some of the advantages and disadvantages of each. So let me just summarize in saying that the selection of pretreatment is a function of the feed water quality, intake system, and membrane fouling propensity. Iron and manganese, DOC or AOC in particular, were key parameters involved in fouling of RO membranes. Plant delivery and operation contracts played a key role in design and operation and performance of membranes. I haven't touched on this, but it's talked about in the report because there are a number of significant non-water quality related issues that can also influence the selection of process. And then finally, an Excel-based tool was developed. Before I end, I'd just like to acknowledge the Water Research Foundation for their funding, our research manager, Kristen Vanderhoevel, our project advisory committee, which provided invaluable comments, and especially the participating seawater RO plants and utility personnel that responded to the questionnaire. So with that, I'll turn it back over to you, Kristen.
Great, thank you, Joe. And now next up we have Dr. Brent Alspaugh. Over to you, Brent.
Thanks, Kristen. I guess first I should make the disclaimer that I'm not a doctor and I don't play one on TV, but I appreciate the consideration in the intro. I'd like to thank everybody for your time here and tuning into the webcast. I've known Joe for almost the entirety of my career, and I'm sure I can speak for him in saying this is frankly one of the best parts of our job. If we have valuable information that can help others out there and an opportunity to disseminate that information, it really makes a lot of things worthwhile. We've almost bookended the desalination process without actually touching on the desal itself, Joe having discussed the pretreatment, and what I'll talk about for my part of the webcast is blending desalinated seawater supplies into an existing regional conveyance system, in this case here in San Diego, and the seawater desal plant in Carlsbad. And also like to acknowledge the Water Research Foundation for their foresight in initiating this research. Essentially, they had an opportunity to explore the blending from the outset of the desal plant operation, which was fairly unique. And not only unique, but the Carlsbad plant is very significant in capacity. When it came online, it more than doubled the existing municipal seawater desalination capacity in the U.S., and so fairly significant in that regard. And we know that there are several other plants planned in California and a couple in other places in the country as well. So hopefully the information we're able to learn from this research will benefit those projects. And there are also some applications that will benefit in terms of brackish groundwater and potable reuse as well, since there are some, obviously, aspects that are unique to seawater, but the core desalination process, in this case RO, is also used in other applications, and so some things would translate there as well. So first, I'd like to acknowledge the research team, which consisted also of Greg Imamura, my colleague at Arcadis, as well as Dr. Jerry Spitel at the University of Texas, and Kristen, our manager at Foundation. And also our project advisory committee that had some excellent input: Wendy Chambers, Dr. Robert Chang, Dr. Christine Owen, Nikolai Vouchkov, who was also involved in Joe's project, and Justin Pickard. And we also had 10 partner agencies on this project that were critical to getting the work done. I show all the names here. I'll highlight Poseidon Water, which is the owner of the Carlsbad Desalination Plant, or CDP, which I'll use throughout the slides. And also the San Diego County Water Authority, which is the regional wholesaler and sole purchaser of water from the desal plant. And then 8 of the County Water Authority's member agencies. And among this group includes those that receive treated water from the County Water Authority, and also those that largely receive only raw water and treat it locally. And we added those to the mix to serve as controls for the research. In terms of background on the project, I could really spend a ton of time talking about that in and of itself, as there are a lot of interesting things to discuss: why the project is important, some of the genesis of the research, and some nuances about how the project was executed. But for our purposes today, I'm really only going to give a high-level synopsis to get people context. So from a high level, what we did was collect data over a 3-year window, and that's the 2 years prior to the operation of the Carlsbad plant. That was calendar years 2014 and 2015, and the plant came online at the end of 2015. And then a 3rd year of data was the 1st year of the desal plant's operation. That was 2016. And then we also collected water quality data that were only obtained by our partner agencies during routine system operation, and we only utilized their existing monitoring locations. And there were a couple of reasons for that. One is that for our partner agencies, their priority is the important work of providing clean, safe, and reliable drinking water to their customers, and to have them go and do extraneous sampling at a number of locations. And the volume of data we would need to really draw meaningful conclusions in that regard was just going to be too burdensome. And certainly the research budget for this project doesn't support a high volume of analytical work, so that wasn't going to be feasible either. So from a practical perspective, it made sense. The second reason was that we wanted to make sure that going forward into the future, our partner agencies and others that would take this research and use it for their own projects would be able to use things that they already analyze. So existing, again, their locations, existing water quality data, and use those tools and only those tools to assess the impact. In other words, it wasn't that we could only assess some very nuanced impact by some eccentric analysis that wouldn't be possible outside of the context of this research. And then in terms of the County Water Authority's treated water supplies, there are a few things that are important to know. They have now 3 sources. Imported treated water comes from the Metropolitan Water District of Southern California's Skinner Water Treatment Plant. And they also have imported raw water, which the Water Authority treats locally at their own 100 MGD Twin Oaks Valley Water Treatment Plant. And now, of course, they have desalinated seawater from the Carlsbad plant, and that supply is piped inland about 15 miles to the Twin Oaks Valley Treatment Plant, and it's blended at that location and then distributed throughout the region via the conveyance. And it's actually, when you get down to it, a little more complicated than that. The imported water supply actually consists of a combination of 2 sources. That's the Colorado River and the state project water here in California, which consists of essentially snowmelt from the Sierra Nevada mountains. And actually, it even gets more complex than this for the number of different intakes for the Water Authority's numerous member agencies distributed throughout the region. And those are details that I've covered elsewhere and don't have time to discuss today. But for our purposes, just to know that the blending situation is complex. In terms of how we conducted the research, we really parsed it in terms of the water quality focus areas that I show here. And if I were only to give you the high-level take-home points from each of these parameters, it would really take up the balance of this time we have today without even the benefit of context to put those into perspective. So what we have done is tried to give this information and disseminate it through a series of presentations over time. For example, we give a talk about nitrification at the WateReuse California annual conference that was last March. We talked about the results for corrosion specifically at the AWWA's annual conference in June. Then we looked at salinity and chloride and boron and the sodium absorption ratio, or SAR, at the WateReuse Association's annual symposium in September. And we've coupled the groups of contaminants together just because of their impact on irrigated plants. I think many people who don't live in San Diego probably just think of us as one more urban suburban pocket in the megalopolis that is Southern California. And to a certain extent, that's true. But probably what people don't know is that we also have a significant component of agriculture to our economy, which represents over $1 billion to that effect. And importantly, I think something like 4 of the top 6 cash crops in our area, things like citrus and avocados, are potentially sensitive to impacts from salinity, chloride, boron, etc. So that's why that was important to analyze for this particular area. And then we looked at the disinfectant residual at the AWW's Water Quality Technology Conference in November. And of course, the research report provides an extensive discussion of those water quality influences in each of those categories. And if anyone's interested, please feel free to follow up with me after the presentation this morning, and I'd be happy to give copies of slides from any of those previous talks if you're interested. But what I'm going to talk about today, with the balance of my time, is the influence of temperature on various parameters. And temperature is something that sort of transcends all of these categories and yet exerts a pretty significant influence in the blended water quality. Before I do that, though, I'm just going to talk about quickly 3 points that are big picture overview water quality findings, just because I think people might be interested. The first is what I'll talk about today, the influence of ocean water temperature, and then how it exerts its influence then on the blend of treated water that's delivered to the water authorities' member agencies. But also, if you've been familiar with the original big seawater desalination plant in the U.S., the one in Tampa Bay, we know from the benefit of that plant that systems on chloramines can see residual decay in their system, and that was induced by the presence of bromide. And so the water authority, knowing that was the case, took some measures in terms of testing in advance, and based on the results of those bench scale testing and a literature review that went with that, they implemented some measures proactively in the design, and it turns out that those measures were successful in mitigating the potential for bromide-induced chloramine residual decay. So that's a positive story. And then finally, one thing we observed is that the introduction of these desal supplies, and that's seawater desalination with reverse osmosis, or SWRO, which those of us in the membrane world use as shorthand, it seemed to decrease fluctuation in several water quality parameters that were interrelated, but all pertaining to things like chlorine residual and nitrification. So, for example, in 2014 and 2015, we saw a certain degree of scatter in those data. But then when the desal plant went into production in 2016, the magnitude of the numbers overall was probably very similar, but we observed a lesser degree of scatter, such that it seemed like the introduction of desalinated supplies had somewhat of a stabilizing influence for those particular parameters. But for today, again, what I'm going to talk about is the impact of ocean water temperature. And although I do discuss this in the research report, in the context of each parameter in turn, the level of depth and the detailed analysis I'm going to show today is not directly addressed in this same format in the report. So for those of you who had the foresight to join the webcast this afternoon, I'm going to give you something that you probably wouldn't otherwise get to see just by the research report alone. Now, there are numerous parameters that are influenced by temperature, and I've listed several of these here. The 2 that I've highlighted on this slide, the CCPP, or the calcium carbonate precipitation potential, and the LSI, or Langmuir saturation index, both those are metrics we're interested in because they suggest the potential for corrosion in the distribution system. For both of these, although temperature does exert an influence, it factors into the formula for calculating those parameters, and that's an important distinction. Because the other parameters I show here, chloride, the TDS, or total dissolved solids, boron, sodium absorption ratio, and the CSMR, which is the chloride to sulfate mass ratio, which is another corrosion-related metric. For these cases, the temperature influences reverse osmosis rejection characteristics, and you'll see that influence in the data that we'll show. So starting with the temperature, here is what the profile looks like and how it varies over the course of the year. The date span here is 2016, so the first full year of operation from the Carlsbad plant. And the yellow line I just showed was the finished water from the desal plant, and I'll keep that same convention in the subsequent slides. So yellow will always represent the finished water. And then you see the blended water supply. That's after the desal water is piped inland and blended with the treated water supplies at the Twin Oaks Valley Water Treatment Plant. That's shown in green. And then the third line here is the temperature at the Water Authority's OTI intake, and that's at the far end of their system. And so it represents an important analysis point for our research in that it's a temporal and spatial boundary condition and represents the longest hydraulic residence time in the system. And of course, that's important for a number of parameters such as disinfectant residual and others. So in terms of key points for what we're looking at here is you see the temperature vary over the season. And interestingly, the blended water quality and the seawater temperature all seem to track very closely. And it's just only by coincidence in this case because there are a number of different anthropogenic and natural factors that influence the temperature of the ocean versus the temperature of imported water supplies from the Colorado River or the Sierra Nevada mountains. But it's just interesting to note that in this particular case, for this year, that those lines tracked so closely together. You can also see, if you look at the difference between the green line and the maroon line, how temperature increases slightly within the County Water Authority's regional conveyance, and that's what you would normally expect. And the range of temperature fluctuation over the course of this year was about 10 degrees Celsius. Now, we know that the temperature fluctuation does exert a significant influence on the finished water quality for seawater RO systems. And because of that, it does influence the blended water quality as well. And that's an important implication that I'll look at in detail with the subsequent slides focusing on various water quality parameters. So starting with chloride, again, here I've got the yellow line, which represents the finished water at the desal plant. And then I've introduced the blue line, which in all the subsequent slides represents the imported supply coming from the Metropolitan Water District's Skinner plant. And what we know is that those represent boundary conditions for the blended water quality, because in not all cases does the Water Authority measure a parameter at the blended water point. And so often what we can say is that the blend is somewhere between the yellow and the blue. And in this case, I've also noted the threshold impact for avocado production. So below about 75 milligrams per liter of chloride, you would start to see impact on the most sensitive plants. So for chloride overall, we see that it does exhibit seasonal variation that tracks very well with temperature, and that is because of fluctuations in the RO rejection. And the magnitude over this first year of operation for chloride varied from about 40 to 100 milligrams per liter. It's a factor of about 2.5. And again, we know because of these boundary conditions that the desal supply reduced chloride in treated water blends in 2016. So the chloride was lower than it otherwise would have been if the Water Authority was reliant on imported supplies only. Then I'm looking at sodium, and you see the same two lines there, imported water supplies and that from the desal plant. And again, sodium, we see that same seasonal variation over the course of the year. In this case, the variation from about 25 to 75 milligrams per liter, or a factor of about 3. And again, sodium, the impact of the desal supply was to reduce the sodium concentrations in treated water blends over 2016. And in terms of the TDS, I have also on this slide added the conductivity simply because it's easy to do and often measured. And people typically will correlate the conductivity with the TDS. And you see the same variation over the season with the temperature. And we would expect that because sodium and chloride together represent about 86% of the ambient seawater salinity. As we saw from the previous slide, we do see that same temperature-related variation. So the peak desal concentration for TDS was about 300 milligrams per liter if you ignore the one sort of large excursion. and that's about half of that for imported water supplies in 2016. The variation over the season was about 100 to 300 milligrams per liter, so a factor of 3. And if you think about it, any given day, the differential between the TDS from the two different sources of supply, the point at which that differential is maximized, then the desal supply represents only about 20% or 1/5 that of imported water. So what we know are two things here. Not only did the introduction of desal supplies reduce the salinity in our system, but it also reduces salinity loading into our basin. So if we didn't have the benefit of the desal plant, we would continue to have a higher level of TDS imported into our region, and that carries over, of course, to irrigation, and it carries over into the wastewater supply, and potentially with impacts for potable reuse as well, which we have some projects in the works here in our area. So not only the quality is delivered to the customer, but also salinity loading is an important benefit that we discovered from this project. In terms of the sodium absorption ratio, if you're not familiar with the formula, I've shown it here in the upper left. The inputs are, in addition to sodium, both calcium and magnesium. And to put it in context, I'll look at calcium and magnesium first, since we've already seen the sodium data. And looking at the data here, I just wanted to point out this one excursion. It's important to note that the purpose of our research was not to diagnose any issues with the plant or explain variations in the data, but it's interesting to point this out just because it stands out from the plot. And you can see this data in the SAR combined data, which we'll go back to in a moment. But really, in this case, as you see, it's not really temperature influence, but the lack of temperature influence for calcium. Sorry, I'm going to get the slide back to where it needs to be. And the reason is that the divalent calcium ion is rejected more efficiently by the desal membranes, and because of that, we don't see that same level of fluctuation in the permeate. It's not observed. Also, calcium levels are about 3.5 times higher in imported supplies than in the desal water. So again, we know that the introduction of desalinated seawater reduced calcium in our treated water plants in 2017, but no influence of temperature here. Then the same thing with respect to magnesium. You see the finished water from the plant and imported water supplies. And just like calcium, magnesium is a divalent cation and thus is more efficiently rejected by RO membranes than the monovalents like sodium and chloride. And so we don't see that same level of permeate fluctuation over the season. Magnesium levels in imports are about 10 times higher than that, or greater than 10 times that of the desal supply. And so again, common refrain, we were successful in reducing magnesium levels in the treated water blend. Then going back to revisit the sodium absorption ratio data, we see that the imports and that from the plant really are fairly close. The magnitude of variation, though, for the desal supply is about a factor of 3, in this case ranging from about 1.4 to 4.3 milligrams per liter. And you see, if you look at the SAR data for the desal supply in October, where it's lowest, that is, you can see the influence of the calcium excursion we showed in the previous slide. But if you average the data for the desal supply over the course of the year, just curiously, it ends up, in this case, being very similar to that from imports, about 2.5 versus 2.6, respectively. Then looking at the CSMR, again, chloride to sulfate mass ratio, there's quite a bit of difference between the desal and imported water supply. We already saw the chloride, so I'll back up and then go to sulfate, what the data look like here. And again, sulfate is a divalent ion, so it's more efficiently rejected, and we don't see that same level of fluctuation with the permeate water quality. And sulfate's about 10 times higher, so we know the benefit of desal supply in this case is that the sulfate concentrations were reduced in treated water blends delivered to our regional customers here in the area. And going back to the CSMR data, I don't parse the details of CSMR in this case, but just to know that for purposes of considering corrosion, higher CSMR values are generally considered to be more conducive to corrosion. And the reason for that is that chloride forms more soluble complexes with lead, and sulfate forms more insoluble scale, which would prevent lead from entering the water quality. So in this case, the CSMR in desal supplies does exhibit variation with temperature, and that's because of the influence of chloride, which does likewise see that same influence, but not the sulfate, which does not. And then the CSMR values are significantly higher than the benchmark values supported in the literature. And the magnitude of variation in this case, as you see, is fairly significant, a factor of about 3.5, ranging from 2 to 7 over the course of this first year of operation of the desal plant. So in this case, the desal supply significantly increased CSMR values in treated water plants in 2016. And what that tells us is there's higher potential for lead corrosion, but it's also very important to understand the potential for corrosion does not mean that more corrosion will be manifested. And in fact, although I don't show the corrosion data here today, we do have lead and copper information for this first year of operation. And in fact, we did not see any impact on corrosion with the influence of the desal supply. And the data for boron are shown here, and I've also thrown the temperature in the plot just again to see how the data track fairly well. We do see that same level of fluctuation. And for boron, it's a factor of about 2, anywhere from about 0.4 the coldest times of the year to 0.8 in the warmer summer months. I don't show the boron levels for the imported water supplies in this case because member agencies aren't required to collect very much boron data. But I did go back and look at consumer confidence reports in the recent past, and those tended to show boron levels for imported supplies ranging from about 0.11 to 0.16 milligrams per liter. Now moving on to the influence on CCPP, or calcium carbonate precipitation potential. In this case, the desal supply has a lower CCPP than imported water supplies in 2016, which means, again, the potential for calcium carbonate precipitation is less, and that would suggest somewhat increased potential for corrosion. But again, not that corrosion would happen, but more increased potential over imported water supplies. Now, in this case, notably, not only do you see the temperature fluctuation with the desal supply, but also in the imported water as well. Again, that's because it's not a function of the influence of RO rejection variation, because, again, calcium being divalent doesn't have that same level of influence, but rather because temperature is an input into the formula for calculating CCPP, and that applies whatever the source water would be. And then the data here for the Langmuir saturation index, and essentially the same key points apply for LSI as applied to CCPP. So overall, assessing the impact of temperature on NFRO systems, it's interesting to note that increasing the feed water temperature, for example, versus decreasing, actually manifests itself in several different ways for an NFRO system. So looking first at the dissolved solids, increasing the temperature means the diffusion coefficient for those dissolved solids is higher. And as a result, you'd see increased salt passage across the membrane, resulting in higher concentrations in the permeate. The feed water also influences the membrane product itself. And if the temperature increases, that means the permeability of the membrane material increases. And that results in both increased salt passage and increased water throughput. And so the net impact on permeate concentrations in this case would be mixed, depending on the specific ions, the temperature impact, the membrane, and other site-specific factors. And the feed water temperature influence on the water itself, and as that water temperature increases, the viscosity of the water decreases, and that means there is increased throughput across the membrane, all other things being equal. And in that case, with increased water means the concentrations of dissolved solids in the permeate would be lower. In a typical system, we would try to operate at constant flow, and in many cases that's the case. And if that's true, then you'd have flow variation, or your pressure would sort of compensate to maintain that constant flow and essentially take the impact on the water itself out of the picture for all intents and purposes. And then that would leave the impact on, getting ahead, that leaves the prevailing influence being the increase in salt passage for the temperature increase, and that results in the net concentrations being higher, which is what we observe in most systems. Now, longtime practitioners of desalination probably understand this is actually a fairly simplistic assessment of what in many cases is a complex phenomenon, but for our purposes today, it provides a useful illustration of why we observe the phenomenon that we do. It's interesting to see the impact of that on the salt passage, and in this table we'll show a few examples to illustrate the magnitude of that impact and how it manifests. So first, if I start off with a feed TDS of, let's say, 2,000 milligrams per liter, and if my temperature were to increase such that the rejection of my RO system changed from a high of 99.8%, let's say it only went down to 99.5%, and then 99.2%. I mean, in terms of raw numbers, that seems like it's not that much of an impact, and you'll see over time, though, perhaps it is in some cases. But for this small 2,000 TDS, you only go from about 4 milligrams per liter in the permeate up to about 16 for the concentrations, percent rejections that are shown here. Then if I increase to 5,000 milligrams per liter for the feed TDS, the numbers increase somewhat, but still fairly small. Up to 10,000, maybe it's small at 99.8% rejection, but if now I'm down to 99.2 because of the temperature impact, then I might expect as much as 80 milligrams per liter in my permeate. And doubling the feed concentration to 20 doubles all the numbers over 10,000, so now the lowest rejection results in 160 milligrams per liter. And then going up to 35,000 milligrams per liter, which is ambient seawater, at 99.8% rejection, maybe I see 70 milligrams per liter of TDS, but if I were to go down to only 99.2%, now I'm up to 280 milligrams per liter, so pretty significant. It's interesting to note, too, that this is a very simplistic illustration because, you know, the TDS consists of not only those things that are influenced by temperature, like sodium and chloride, but also those things that are not, like calcium and sulfate. And so these numbers are probably conservative, but nevertheless illustrative for the point. And now, summing it all up, I have what I've just called an amplification factor by virtue of having that temperature influence. So it's about 2.5 times if I only go down to 99.5% rejection. But if I go down to 99.2% rejection, I see the concentration amplified by a factor of 4. Referencing back to the 2000 case, you see a large percent change, that is the amplification factor, but the magnitude of the change is actually relatively small. But then in the case of seawater, I have that same percent change, but a larger magnitude of dissolved solids in the system. And summarizing what we observed in this research, going down the list, boron, a factor of about 2, chloride, 2.5, the chloride to sulfate mass ratio, 3.5, and then 3 for sodium absorption ratio, and the TDS. And all of that is true for a temperature variation of about 10 degrees Celsius. So the implications of this are, of course, be attentive to temperature in your system. And it's important to think about the temperature for RO design. In the cold water case, what we would do is use that coldest temperature to size the system to make sure I have sufficient throughput under what might be the most limiting conditions. So, for example, if I were to size my system under a much warmer temperature condition, but then the temperature dropped, I'd either be expending a lot more energy than I thought to obtain the capacity that I need, or having to potentially be limited in the capacity if my pumps can't do the pressure that's required to give me that output. In the warm water case, you want to ensure you look at that because you may have particular permeate quality that you're interested in. And it's of particular interest for cases of high feedwater TDS, like seawater, which we studied in this project, or in the case you may have stringent permeate concentration targets, which might be the case for, say, potable reuse. Typically, NFRO system designers are pretty good about the former in terms of sizing the system to make sure the throughput is adequate to generate the required capacity. but we're not always as careful to account for the warmer water case. And there are some good reasons for that. Historically, most of the applications for RO, at least in the U.S., have been for brackish groundwater desalination. And typically for brackish groundwater, the TDS concentrations are much lower than for seawater. So if I'm only talking about 2,000 milligrams per liter or 5, then if my TDS concentration in the permeate goes from 4 to 16, for example, I don't particularly care because I'm good either way. And similarly, with the brackish groundwater supply, I don't expect the temperature to change all that much. So perhaps temperature is an afterthought that you might think twice about making sure that you consider. It's also important to note that even though the temperature for brackish groundwater might not change, in a case for potable reuse where you're using a wastewater source, you would see some kind of temperature variation seasonally throughout the year. And you might, again, have those more stringent permeate concentration targets that you're interested in. So in this case, you'd certainly want to be more attentive to that temperature swing than perhaps most of us would be. So as a final message, just to be very diligent about the details in non-standard RO applications because temperature can be an important consideration. And with that, I'd thank you for your attention, and I think we have some questions now, perhaps.
Thank you, Brent and Joe, for the excellent presentations. Now we're going to go ahead and open it up for question and answer session. We have about 20-25 minutes. So please remember to type your questions into the chat box on the lower left-hand corner of your screen, and we'll go ahead and get started. So I think our first question here is for Joe, and we've received a few questions about SDI. What kind of SDI test are you using? That is, how are you getting such high numbers as the standard is SDI 15, where max is 6.6?
That's a good question. For the plants that we worked with, they were primarily using SDI 15s for their when they were looking at their feed water into the RO membrane. However, as the questioner points out, and it's a good point, is how do you get such high SDIs out of that? Because traditionally you cannot do that. And so for and most of those high SDIs, or almost all of them, were primarily associated with the water that was coming into the plant. And under those conditions, most of the plants conducted them using SDI 5s because they could not put that much through there. And so when comparing the data, obviously you have to take that into consideration. But generally what they were trying to show was that it was performing, it was removing the materials from the influent water to produce an SDI that is applicable to RO.
Thank you, Joe. Our next question is for Brent. Did you see a relatively constant ratio between chloride, sodium, TDS, and conductivity?
Yeah, it's an interesting question, although in this case we didn't track that because knowing that information wouldn't necessarily have been pertinent to assessing what the impact and the water quality would be in the system. But if we need to know that, we certainly can. We have the data and can go back and look at those ratios if it's necessary.
Thank you, Brent. Another question for Joe. Can you please talk a little bit more about the removal of boron?
Sure. Boron in some plants, particularly those that were located in the Mediterranean, is an important constituent to be removed because boron, much of the water is used for irrigation purposes, and boron is not compatible with various species associated that are grown there, well, grown everywhere. It's an issue in the U.S. too. So those plants had a boron concentration limit of 1 milligram per liter as a final product water level of that particular constituent. Now, to get to that, however, in one plant, the membranes were just not doing well enough. So they were forced to either blend with groundwater supplies, but more importantly, what they were going to do was to, as they begin to replace membranes, replace them with membranes that are more boron specific, that can remove higher levels of boron, so that they wouldn't have to go to alternative measures to meet that boron level, which is quite frankly their primary constituent that they're concerned about.
Hey, Kristen, can I add something about boron in particular?
Sure.
I think for those on the call or the webcast that are RO experts, this is probably not news, but for many people who don't particularly know why RO has difficulty removing boron. And historically and throughout the world, boron has sort of been like this key parameter that's very difficult and one of the major challenges of accomplishing seawater with RO. And the reason why boron is challenging is because RO, one of the main ways that RO rejects dissolved solids is by charge. And at ambient seawater concentrations, the boron is in this fully protonated form, so it's not a charged species, and therefore the RO membrane doesn't reject it as well. I think if you increase the pH in your system above 9.2, then the form of boron is the borate ion, which is much more efficiently rejected. And in some cases, plants might have a first pass, and then once they've taken out many of the scaling ions, it would potentially be problematic at higher pH. Then they would adjust the pH up and then use a second pass to eliminate the boron. But just one way to skin that cat, so to speak. But that's the reason why boron tends to be problematic.
Thanks very much, Brent. And another question for you. What impact does temperature have on the rejection of emerging contaminants such as pharmaceuticals and personal care products?
Yeah, that's an interesting question too, because in this case we looked at dissolved solids, but it's important to understand that those same influences, how the membrane gets more permeable and the diffusion coefficient goes up, would also apply to those emerging contaminants, whether they're things like pharmaceuticals and personal care products or things like PFOA and PFAS, which are prominent in the water industry today. So again, probably seawater maybe isn't such a big concern, but I think for other applications like potable reuse, and certainly you want to take into account temperature. Unfortunately, things like PFOA and pharmaceuticals can't be modeled with the typical tools that we use, and so you probably want to do piloting in order to determine what the impact might be, and make sure that you're getting the rejection that you want at the full range of temperature that you would observe.
Thank you very much. And we'd also like to pose that question to Joe. Have you also considered the removal of emerging contaminants in your projects?
In this particular study, they weren't looked at because that wasn't a primary focus of it. But certainly, we've looked at in other Water Research Foundation studies, and it's RO for the most part does a very good job in removing many of those emerging contaminants. Some of the things that it doesn't remove are some things that are not considered contaminants per se. But for these main plants, the major contaminant was boron.
Thank you. And I do also want to point out we do have, as Joe mentioned, other research studies looking into emerging contaminants, and I encourage you to check out our website for those studies. Our next question is for Joe. Did any of the plants use methods other than SDI, such as MFI?
All of the plants use primarily SDI, but it's acknowledged that MFI can be, in many respects, a better parameter, although it takes a different methodology to do it. And there's also a number of MFIs, different MFI types of fouling indices. In fact, we've developed one ourselves in our lab, but for this particular study, they focus primarily on SDI.
Thank you. And a question for Brent. Did you look at TOC, DOC rejection by RO as a function of temperature and its impact on DBPs?
We did not. We did look at DBPs because that was something that all the utilities in our study were concerned with. And obviously the RO is very efficient with taking out TOC, and as a result, even at the far end of the system, we used a complete set of DBP data for an entire year as a case study, and the disinfection byproducts were very low. I want to say in the teens, and the HAAs were probably below 10. So even though we didn't look at TOC specifically, we did look at the DBPs, and it was actually very good impact from the desal water supply.
Thank you. This is another one for Joe. Did any of the utilities or facilities surveyed in the pretreatment assessment use continuous chloramination of the pretreatment system to control biofouling?
Yes, one utility did use chloramination, but for the most part, they all used chlorination. And of course, the advantage of the chloramination is that it doesn't have the high potential for reacting with the TFC membranes that are employed, and so it becomes a necessity to quench that chlorine before it actually hits the membrane, and that's been a lot of the challenge. Chloramination is routinely used over the RO membranes in water reuse applications. Probably has more precedent in looking at recycled water than it does at seawater RO.
Thank you. And another question here for Brent. How much impact would temperature have in potable reuse applications? I think you touched a little bit on this, but can you provide more information?
I think it's hard to say a priori, and of course it would depend on a number of things. How much the temperature swings in any application. It would depend on what the feed water quality is, and then what the permeate goals are as to whether or not in any given case, whether temperature would, I guess, play a significant role. And then, of course, significant is also dependent on what your goals are. So I think it certainly does have an influence, but whether or not it's influenced to the point where it's a concern is something that needs to be analyzed on a site-by-site basis.
Thank you. And our next question is about another emerging hot topic, microplastics. And the question is, how are microplastics impacting seawater RO pretreatment systems?
That's a good question. I'm not sure I know the answer. I don't know that the answer is out there, but I would think intuitively that based on microplastics interaction with the membranes, because of the vast difference in size, that they would be rejected and not necessarily have a great impact upon the MF performance. If you look at traditionally, we look at colloidal materials. The colloidal material has to be around the size of the pore size in order to get into those pores and adhere, where the microplastics are much larger. We are starting up a study now to look at that exact issue, that microplastics and removal essentially through the different membrane processes, which through a recycling plant, and that hasn't been done before.
Great, thank you. Our next question is back to Brent. Does the Carlsbad desal plant have the correlation coefficient numbers available for each water quality parameter to the temperature?
I'm not sure what is meant by the correlation. My guess is they probably don't normally calculate that, although there's no reason why they couldn't if they needed to.
Okay, thank you. And another question for you. Was there any difference between the DBP speciation in the feed and the permeate water of RO? Did you observe more of the brominated compound in the permeate?
So the latter question is probably the most interesting one, in the sense that we did specifically try to see before and after the desal plant went online whether or not we had increased occurrence of more brominated species of DBPs, thinking that because there is a higher concentration of bromate, not only in the source water, of course, in the sea, but even in the permeate, there's a relatively high concentration of boron, or bromide rather, relative to other supplies. And curiously, we did not actually in the one case study that we did, going from before the desal plant came online to after. There was essentially no detectable difference in ratios of one type of, let's say, brominated species versus the more chlorinated analogs.
Great, thank you.
Just to add on to that, for RO permeate, the relative level of total organic carbon is so low that to see differences in speciations, it would probably be pretty difficult because the overall concentrations of potential to form organic halides is very low to begin with. So any changes you'd see would be, in terms of overall concentration, would be very, very small.
Yeah, and I think that's pretty consistent with what we saw too.
Thank you. And a question here just came in for Joe. Does the pretreatment tool assume coagulant would be used with membrane pretreatment, or does it have the option to use membrane pretreatment without coagulant?
So the coagulant in the tool is chosen by the feed water characteristics. And so depending on what the feed water is in terms of carbon and other materials, the tool itself, and based on those buckets that we put those particular precursors in, based on that, it'll determine whether a coagulant is suggested to be used or not in the process. So the tool actually does that for you. And obviously, if you have a very clean water, you wouldn't necessarily need coagulant to be employed. But if you have water with a high algae count, of course, coagulant would be employed.
Thank you very much. And a question for both of our presenters. Did the projects look at brine management issues, in particular corrosion or scaling potential problems?
Well, for our project,
go ahead,
Joe.
No, please.
Well, the short answer is no, we didn't look at concentrate management. That wasn't a part of the study, strictly speaking, in the distribution system and the finished water quality.
In ours also, it wasn't a big issue, but it did only if there was a discharge permit issue associated with discharging a certain concentration of that brine, then it became an important parameter for those utilities to consider. And in some cases, what it forced them to do was to actually have very low feed water recoveries so that their concentrations of their brine and constituents in their brine were low enough so that they could go ahead and discharge it.
Thank you. And another question for Joe. The Dynasand filters are not in the Excel sheet. Is that due to their poor performance in the pretreatment?
Well, for a couple reasons. I think Dynasand, for the most part, is the exception to the rule of pretreatment. I only know of a couple of plants worldwide that employ Dynasand as a pretreatment. And secondly, there are a lot of operational challenges associated with Dynasand, using Dynasand filters. And thirdly, we wanted to limit it to the two, I guess, most promising pretreatments and more widely used pretreatments that could potentially be employed for RO.
Thank you very much. And our next question is, for the plants with no AOC that had subsurface intakes, were the intakes below the sea floor? And if so, do you think that absorption played a role in reducing AOC?
First answer is yes. The second answer is absolutely. I think TOC will absorb onto the material which makes up the sea floor. We have done in similar studies, not necessarily with seawater, but looking at various different types of materials and looking at the absorption of organic as well as other materials, and you can see an impact on that. So the short answer is I think, yeah, they do play a role. It does play a role.
Thank you very much. And one last question I'd like to pose to both of our speakers today to end out our session. What is the biggest takeaway or lesson learned during each of the studies that you conducted? Brent, would you like to start us off?
Sure. I think one thing that doesn't necessarily apply to the temperature influence, but Joe mentioned this in his talk as well, and didn't cover it like I didn't. But for the treated water quality, there are contractual things for these plants are often big and complex, and the transactions that govern how water is produced and how it's purchased, et cetera, they're pretty significant. And there were, in this case for the Carlsbad plant, there were contractual provisions that had implications for blended water quality. And that's not to say that they're good or bad, but it's, I think, an important take-home to make sure you're thinking about upstream, even things that you might not think about that have impact on water quality downstream. Try to connect the dots upstream to say, hey, in case this does have an impact, and if it's adverse to what I'd like, maybe I should think this through a little bit.
And from my perspective, I think as I started off, I said, the three most important things for assuring successful seawater RO performance is pretreatment, pretreatment, and pretreatment, and I think that continues and will continue to be true. With that in mind, I think one of the biggest aspects of the appropriate pretreatment is to really get a handle on the water quality that will be employed by the plant. And because what often happens is if water quality is only observed over a certain part of the season, one may miss some parts of the year where there could be a degradation of that water quality, which will impact the pretreatment process selection. And in terms of water quality, of course, it's also really important to understand whether there's an algal influence on that water that the plant will be using, because that could drastically change, one, the kind of pretreatment process that you would ultimately design, and of course, how well that RO will perform when that algal bloom or other harmful algal matter occurs.
Thank you both, and a special thank you to both of our speakers today for their excellent presentations. You can find more information on our desalination work, upcoming webcasts, and download the studies that were mentioned today in the program on our website at waterrf.org. Please stay tuned for the survey questions, which will appear on your screen momentarily. Thanks all.